Hey folks, we are back with the Unit 3 Day 9 lesson, and this is the second video. We're going to go through some examples now and look at how we can solve for the point of intersection or determine if there is a point of intersection of these sets of three planes. So in the first one, I'm given three equations, and I have 2x plus y plus 6z minus 7, 3x plus 4y plus 3z plus 8 equals 0, and x minus 2y minus 4z minus 9 equals 0. So I always just kind of get in the habit of listing out the normals because that's a really important thing to do. Like I said in the previous video, you've got of the 8 different cases, 5 of those 8 don't require you to actually do a solution with all three equations at all. 5 of these different cases are going to be either kind of a trivial case where there's no solutions, or a case where you maybe are just dealing with actually two planes. So here you want to check and make sure that none of the normals are scalar multiples. If they are, it's a whole different thing, and then you need to kind of change your method. But these are not. So none of the normals are scalar multiples. From here, I would work this problem like it was one of the questions in day 8, where we're going to solve this using matrices. There are ways of solving this just kind of with repeated substitution and elimination, but personally I find it gets really messy. So I'm going to use matrices. Like I mentioned in lesson 8, because I've got this third equation with a 1, I'm not going to write this at the bottom. I'm going to swap the first and third equations, and I'm just going to kind of use an arrow to indicate that that's what I'm doing so that somebody looking at this could follow my work. So I'm going to set up my first row of my matrix with the coefficients of this bottom equation just because it's already a 1. Why not save yourself a step? 1, -2, -4, and now careful, because in standard form this is not equal to something. It's all equal to 0. So remember, we have to kind of move that over and make that equal to +9. I don't feel like you need to write that out. If you do, obviously that's fine though. So here I have 3, 4, 3, and then when I bring that over to the other side, it would be -8. And then the last one that I'm swapping down is 2, 1, 6, and bring that over, it's +7. So I've got my matrix set up here. I am going to take a look first. And the first step, remember, was get a 1 in that top corner. That's done. So now I can work on getting zeros. Step 2 was zeroing out here. So for row 2, it's going to equal the old row 2 minus 3 times row 1, because I have to get a 0 there. And my row 3 is the old row 3 minus 2 times row 1, because I have to get a 0 in that bottom corner. So I'm not changing anything in the first row. 1, -2, -4, and 9. Now I'm going to take, for row 2, I'm going to take these ones and subtract 3 of the row above it. So 3 minus 3 times 1 is 0. 4 minus 3 times -2. So again, please make sure you're being careful. You can use a calculator. You can write this out. 4 minus 3 times -2. So that's +6. So I'm going to have a 10 there. And 3 minus 3 times -4. So that's +12. So I've got 15, -8, minus 3 times 9. And I've got -35. In the third row, I am taking the old numbers and subtracting 2 of row 1. So 2 minus 2 times 1 is 0. 1 minus 2 times negative 2, so plus 4, is 5. 6 minus 2 times negative 4, so 6 plus 8, I get 14. And 7 minus 2 times 18, 2 times 9, pardon me, is 18. 7 take away 18 is negative 11. Okay, so again, just being real super careful with your calculations, write it off to the side or use a calculator. Now, I am going to get, unfortunately, a little bit of a mess with my fractions here. I'm going to have to take this and divide it by 10 to get step 3 and to get a 1 in there. Now, in general, I would really encourage you to use fractions, but especially something like this, where you've obviously dividing by 10, we're going to get some nice clean fractions. I would never round a fraction, but if you have things like 0.5s, it's actually probably fine. And maybe just kind of for ease here, I will say row 2 is row 2 divided by 10, and actually just make those 1.5 and negative 3.5 when I divide. So I have 0, 1, 1.5, and negative 3.5 there. Okay, now I want to kind of go through step 3 and 4 all together here. So I have a negative 2 in this spot, and I want to add 2 1s to zero that out. So I'm going to say row 1 is row 1 plus 2 times row 2, and that'll get me a 0 in that top middle spot. So 1 plus 2 times 0 is 1. Negative 2 plus 2 times 1 is 0. Negative 4 plus 2 times 1.5. So 2 times 1.5 is 3. Negative 4 plus 3 is negative 1. And then 9 plus 2 times negative 3.5. So 2 of these is negative 7. 9 plus negative 7 is 2. So we actually don't get such messy numbers as we maybe thought we could have here. And then I'm going to have to get rid of this 5. So I'm going to be subtracting 5 times row 2. So row 3 is row 3 minus 5 row 2. So here we've got 0 minus 5 zeros is still 0. 5 minus 5 times 1 is 0. 14 minus 5 times 1.5 is going to give me 6.5. And I'm on my calculator at this point because I don't want to get mixed up. And then negative 11 minus 5 times negative 3.5 is 6.5. And that works out really nicely. We could have obviously done this with fractions. Again, if you've got something like an over 3 or something, or multiple decimal places that are going to get messy, I would never ever do decimals. But if it's 0.5s and that's it that you're working with, it's kind of okay to do that. So now I'm going to do step 5, which is to get a 1 in this spot. So I'm going to say row 3 is equal to row 3 divided by 6.5. And I've got 0, 0, 1, 1. Now I can eliminate these ones. So row 2, or row 1, I guess I'll do first. Row 1 equals row 1 plus row 3, because that negative 1 plus that positive 1 will zero it out. So here I have 1 plus 0 is 1. 0 plus 0 is 0. Negative 1 plus 1 is 0. And then 2 plus 1 is 3. So that's all set. Then row 2 is going to equal the old row 2 minus, because I have to zero out that 1.5, 1.5 times row 3. So here I have 0 minus 1.5 times 0 is 0. 1 minus 1.5 times 0 is 1. 1.5 minus 1.5 times 1 is 0, which the end math gets a lot nicer here. And then negative 3.5 minus 1.5 times 1. So that's going to be minus 1.5, and that gives me a negative 5. So here, this comes up with a solution really a lot like what we saw in the day 8 lesson. So we have a solution that is a point. So we have x equals 3, y equals negative 5, and z equals 1. So the solution is a point, because that's what that information gives us, and it's the point 3, negative 5, 1. So we've gone through our calculations and come up with that as our solution. In the next example, we're going to kind of go through a similar situation. We're going to go through this and try again to solve, but it's going to actually come out a little bit differently. So again, just like I said before, we're going to always write out my normals just to show really clearly that it's not one of the first 5 cases. So we can clearly see none of these normals are scalar multiples of each other. That's not something that that I'm dealing with. I don't have scalar multiples there. So this is one of the last 3 cases. It's case 6, 7, or 8, and we have to work through the solving to see which case that is. So here we are in kind of good shape already, because we are going to have a 1 as my coefficient up there when I do my matrix, so I'm not going to change them around at all. So my coefficients here are 1, negative 5, 2, and when I bring that negative 10 over, it's going to be positive 10 on the other side. The next equation gives me 1, 7, negative 2, and then negative 6 on the other side. And then the third equation is 8, 5, 1, and with a positive 20. Because you'd have to bring it over to the other side of the equal sign. So going through this, again, I've got step 1 finished already because I have a 1 in that spot. Step 2 needs me to clear out these 2 terms and get a 0. So to get a 0 here, I'm going to say row 2 is equal to row 2 minus row 1. Sometimes people ask me, like, does it matter whether you write this above or below that arrow there? It doesn't matter. I write them, and I think it's good practice to write them in the order that you're actually doing the calculations, but I just kind of put them wherever it fits. It's not a big deal either way. So here I'm subtracting row 2 minus row 1, so here I get a 0. 7 minus negative 5 is 12. Negative 2 minus 2 is negative 4, and negative 6 minus 10 is negative 16. And then for row 3, I have to subtract 8 times row 1. So 8 minus 8 times 1 is 0. 5 minus 8 times negative 5. So that's plus 8 times 5 is 40, so it's 45. And then 1 minus 8 times 2. So 8 times 2 is 16. 1 minus 16 is negative 15. And then 20 minus 8 times 10 is 20 minus 80, so that's negative 60. So again, super careful. It's probably a miracle if I do this video without making an error, and we'll just see how it goes. So in here, I know I need to get a 1 in that middle spot. I don't really want to divide by 12, but I guess I will if I have to. Likewise, I don't necessarily want to divide those guys by 45 because I'm still going to end up with some fractions. So if you could divide out this one, then it's a good idea to swap equations to avoid fractions, but you can't always. So we're just going to kind of tough it out here. I'm going to do row 2 is row 2 divided by 12. So here is one where we can't, as much as we maybe would like to, just make things a decimal. Obviously, we're going to have 0, 1, negative 1/3, and negative 16 over 12, which is negative 4/3. So that other one where it was 0.5s, I would maybe change to a decimal, but of course you can't do that here. So then we need to clear out the numbers above and below, like that negative 5 and 45. So for row 1, I have to get rid of a negative 5. I'm going to add 5 ones. So row 1 equals row 1 plus 5 times row 2. Now, since I already did the divide by 12, having this written down here means that I'm going from the new numbers. I'm not going to try and do it with those old ones. So again, you're going to need to be super careful with your calculations, especially once you get into fractions. So here I have 1 plus 5 times 0 is 1. Negative 5 plus 5 times 1, oops, I made a dot there, is 0. Now I'm going to have 2 plus 5 times negative 1/3. And that is a great example of when to use the fraction button on your calculator rather than risk making little mistakes, and that's 1/3. And then I have 10 plus 5 times negative 4/3. So 10 plus 5 times negative 4/3 is 10/3. So I'm getting a little crowded in there. I should have made my matrix bigger dealing with fractions. Then we're going to do the same deal for the row 3, except now I've got 45, which is, you could actually divide out by 15 and get like a 3, negative 1, and negative 4, and that would be a lot easier to deal with, but I'm just kind of too lazy to write it out again. So row 3 equals row 3 minus 45 row 2's. We'll deal with it on the next step. So here we've got 0 minus 45 times 0 is 0. 45 minus 45 times 1 is 0. This is a calculator. Negative 15 minus, actually this is not so bad. Negative 15 minus 45 times negative 1/3 is actually 0. Whoa. Then let's do this one. Negative 60 minus 45 times negative 4/3. That's 0 as well. So we've come to something different that we haven't seen yet when we've been solving matrices. Maybe you have seen it, but if you did, it may have been a calculation error in one of your previous homework assignments. So here we've got a whole row of zeros. And the question I like to ask here is kind of to think about, what does this mean? So what does this mean? And how many cases does 0x plus 0y plus 0z equal 0? How often does that happen? And hopefully you can say, oh, there's an infinite number of cases where 0x plus 0y plus 0z equals 0. There's actually infinite number of points that satisfy that equation. So there's an infinite number of points So which of those cases from that group 3 where we didn't have collinear normals had infinite points of intersection? It's going to be this one. There's an infinite number of possible intersection points because these 3 planes intersect in a line. So here, this tells us that it's case 7, intersect in a line. Okay, so now we know that we have a line of intersection. We have to figure out what that line of intersection is. So we know we're going to have something with a position vector plus a scalar multiple of our direction vector. That's what the equation of a line looks like. And we know that there's an infinite number of choices for the position vector. There's an infinite number of choices for the direction vector. This could be any point on the line, and this could be any scalar multiple. So we've got our position and our direction, but there's infinite choices. And this is going to go back to something that we did in the intersection of 2 planes. Just to make our lives easier, I'm going to choose the point on the position vector where z equals 0. I'm going to choose the point where this line passes through the xy plane. And I'm going to choose the direction vector that's a scalar multiple where the z component is equal to 1. So here, I'm just going to say let z equals 0 plus 1t. It's pretty arbitrary. You don't have to do that, but it ends up working out pretty nicely and cleanly compared to the other things. So here, we know we have something where z is 0 plus 1t, or z just equals t. Okay. Now, we want to figure out what x and y are here. I'm going to go back up to row 1 and say x plus 1/3 of z equals 10/3. But I said pretty arbitrarily, let's have a position vector where z is 0 and a direction vector where z is 1, so z just equals t. Now I can sub in my z equals t here. So x plus 1/3 t equals 10/3, or x equals 10/3 minus 1/3 t. So that is my second, and I'm getting my parametric equations here. So that's one parametric equation, that's another parametric equation, and I'm going to do from this the middle row, pardon me here, I'm going to find a parametric equation for y. I know that y minus 1/3 z equals negative 4/3 from this middle line. So if z is t, y minus 1/3 t equals negative 4/3, where y equals negative 4/3 plus 1/3t. So those are my 3 parametric equations. I can just take them and put them into the vector equation. So the position vector has an x component of 10/3 and a y component of negative 4/3. And the direction vector has an x component of negative 1/3 and a y component of 1/3 and a z component of 1. So that comes up with my line of intersection. The big thing here is at this step, when you get this big row of zeros, thinking, what does that actually mean? And how often is that true? It's always true. There's an infinite number of points where 0x plus 0y plus 0z equals 0. That's true for an infinite number of possible points, all of the points on that line. Okay, so now we've gone through the example number 1 where we had the case number 8 and it intersected at a point. Example number 2 where it intersected in a line and we had infinite points of intersection. Now we're going to look at example number 3 and hopefully you guys can probably guess what's going to happen here. And we'll just kind of see what that looks like when we go about trying to solve. So again, always writing out my normals because you just never know. So here my normals are 1, 3, -1, and 2, 1, 1, and 1, -2, 2. So again, pretty obviously we can take a look at those, and I don't have any scalar multiples. None of these planes are parallel or coincident, so I don't have any of the first 5 cases. Going to put these equations into a matrix, and again, I've kind of organized it that I have a 1 in the first equation, which is going to make my life a little bit easier. So I'm not going to have to rearrange my equations. The first one, I've got 1, 3, -1, and then when I bring that guy over, it'll be -10 on the other side. So 1, 3, -1, and then on the other side of the equal sign, -10. Second equation, I have 2, 1, 1, and then a +8 when I bring it over. And the third equation, 1, -2, 2, and a -4 when I bring that over. So as I said before, step 1's already done. Step 1 is to get a 1 in the top left corner. Step 2 is to zero out the rest of that row. So here I'm going to take the row 2 and subtract 2 of row 1. So row 2 equals row 2 minus 2 times row 1. And row 1 is not changing, so I can fill that in. Now 2 minus 2 times 1 is 0. 1 minus 2 times 3 is -5. 1 minus 2 times -1, so that's +2 is 3. 8 minus 2 times -10 is 8 plus 20, or 28. And then for row 3, I have the same coefficient, so I can just say row 3 is row 3 minus row 1. So 1 minus 1 gives me 0. -2 minus 3 is -5. 2 minus -1 is 3. And -4 minus -10, so plus 10, would be 6. So that's step 2. Step 3, we're going to go through and get a 1 in that middle spot. And I think you guys can kind of already a little bit see what's happening when we have this here. Now, normally, you know what? Normally I would go and get this, but if you see this happening, so here we have -5y plus 3z equals 28, and -5y plus 3z equals 6. I feel like that's unlikely to happen, right? Like unless x and y are both 0. No, that wouldn't even work. There's no cases. I don't even know what would be happening there. -5y plus 3z can't equal 2 different things. So I'm going to actually just kind of go out of order and not get a 1 there. I'm just going to say row 3 equals row 3 minus row 2, because I'm just going to skip ahead to the zero this out and skip the messy fraction step. If you didn't do this, if you just kind of did the same process, it would 100% still work the same, but you just end up with kind of some fraction issues. So here I have -5 minus -5 is 0. 3 minus 3 is 0. 6 minus 28 is -22. So this is the row where we've kind of like lost all of our coefficients. And we have to think, what does this mean? So here What does it mean? How often does 0x plus 0y plus 0z equal negative 22? Does that ever happen? It doesn't. So never, no intersections. Unlike the other one where 0x plus 0y plus 0z always equals 0, there's infinite points where that's true. This is never true. So this is case number 6. And then you can just end there. You just say that there's no intersections. There's no solution to this system. Okay, so you just write no solution. And you could put, actually, normally, I do actually typically give an image, like the pictures of those 8 cases, and just with numbered cases, no math, just those diagrams, and you would have to tell me which case it was. So in that one, we kind of end off early. We don't have to find the equation of the intersection of a line like in case 7. We just get to this part and say, well, that's never true. I don't have any intersections. Last example for this lesson. We, again, always writing out your normals. Find the intersection of these 3 planes. So N1 is going to be 4, negative 2, 6. N2 is negative 10, 5, negative 15. And N3 is 6, negative 3, 9. So hopefully you guys see a pattern here that the x coordinate is double the y coordinate, or negative 2 times, and the z coordinate is negative 3 times, and that's kind of the same scalar multiple. So we could say n1 equals, I might say 2 times 2, negative 1, 3, n2 equals negative 5 times 2, negative 1, 3, kind of looking at the lowest common multiple of these parallel vectors. And this one, n3 equals 3 times 2, negative 1, 3. So these are, the normals are all collinear. If all 3 normals are collinear, then that's one of the first 3 cases. And we just have to kind of confirm, are these written in standard form? So could you divide out and rewrite these equations in a better form? So here we could divide this by negative 5 to put that in standard form. So my planes are going to be just kind of confirming in standard form. So plane 1 is in standard, 4x minus 2y plus 6z minus 35 equals 0. There's no common factor. I don't have fractions, and my leading coefficient is positive. Plane 2, I can divide out a negative 5. So I've got 2x minus y plus 3z plus 4 equals 0. But that's still not the same. We obviously can tell that these are different planes when we get them in standard form. And here I have a common factor of 3 in the normal, but I can't divide that 3 out of my d value. So that was in standard form already. So just kind of confirming, rewrite in standard form if you need to, and then we can say no solutions. These are all parallel planes. And that is case number 1 from our diagrams. And that's it. So all of the case number 5s, 1 to 5, would follow a similar kind of solution as this. The one with the two collinear or coincident planes and one cutting through it would need some work, like that day 7 where we were finding intersection of two planes. But generally, you're just going to kind of analyze the normals, say whether the planes are parallel or coincident, and list your case number for any of those first 5. And that is it for day 9 and 10.